Hello, AP Stat. Let's talk a little bit about the chi-squared distribution today. All right, so in previous chapters, for example, in our last unit, we talked about means. In Unit 6, we talked about proportions. So we have talked about testing hypotheses about one population proportion. We have talked about testing hypotheses about two proportions and two means. And we've talked about the difference between paired data sets. In this chapter, what we're going to be concerned about is not one value, like one mean or one proportion, but we're actually going to be talking about the distribution of a categorical variable, which means I'm not concerned with one slice of the pie, I'm concerned with the whole pie. So again, it's not just one little proportion, it's the set of proportions, the distribution of proportions that add up to 100%. So basically, we're going to be looking and saying, does this set of proportions match what I think is supposed to be true about the set of proportions in the population? Or we may talk instead about, does the set of proportions in population 1 match the set of proportions in population 2? Okay, and we also are going to talk about a topic of independence. And so we talked about independence before with segmented bar charts. And so now we're going to formally discuss that independence. All right, so in order to do this, we're going to be using something called a chi-squared test. Now, in your textbook, this is section 12.1. In AP, it is 8.1. So on chi-squared data, you're looking for a distribution of categorical data, which means you're going to have a bunch of counts for a categorical variable. For example, one kind of categorical variable might be, do you plan to pay your taxes using a credit card? And 100 people were randomly selected. They definitely will, probably not, probably definitely will not, right? You have these four responses, and here are our counts in there. There's our 100. So when you go to look at this, there are a couple of values that you need to be able to pick out from one of these categorical things every time you see one of these frequency lists, okay? The first is, you always want to ask yourself, how many categories of this categorical variable are there? Or in other words, how many subcategories, how many answers are there? So in this case, definitely will, probably will not, probably will, definitely will not. I can't say that right. Those are four categories. There's four categories. And the other thing we need is how many, what is the sample size that was taken? And we're going to do that by adding the frequencies, 14, 12, 24, and 50. That gives me 100. Okay. Or for example, what color are Skittles? So we take a randomly selected bag of Skittles and we take them out and we count that there are 23 red, 28 orange, 27 yellow, 39 green, and 33 purple. So if you add those together, there were 150 Skittles in the bag. That's sample size. That's going to be N. All right. So let me see if I can get my little pen up and running here. All right. So again, that's N over here. N over here is that 100 total. There's that sample size there, okay? And the other thing about this is that the red, orange, yellow, green, purple part of this, those would be our categories. So there's 1, 2, 3, 4, 5 categories. And as for vocabulary, 23, 28, 27, 39, 33, these are called observed counts. So this is what we actually went out and saw. This was the actual thing we saw with our eyeballs, the observed counts. Over here, 14, 12, 24, and 50, those are observed counts. Now, categorical variables, that data is not numeric data, so you can't take a mean. It cannot follow a normal distribution. And if you have several proportions, you can't use the sampling distribution of p hat because we have several proportions. So we're talking about all of the proportions together. So instead, what we're going to do is we're going to use something called the chi-squared distribution. Now, notice the pronunciation of that chi. This is this Greek letter, which kind of looks like an X. Okay, so when you go to draw that Greek letter, it's like almost like a curvy X. So it's a chi-squared. Okay, so not a it's not a what am I trying to say? Like chai, like don't say it like T. So make sure you don't pronounce that hard CH there. It's chi, like yippee-ki-yay, all right? So the chi-squared test statistic is something that is on your formula sheet. For example, if you look at the front side of your formula sheet, down at the bottom where you see the standardized test statistic and where you see the confidence interval formula, you're going to see chi-squared. And what it says is it is the sum of, which means you're going to do this for everything you have, the observed minus the expected squared divided by expected. Now, observed what you actually see. So up at the top, that's that 23 and 28 and 27, etc. Okay? So to figure out what the expected counts are, well, you are already pros at computing expected counts. Expected counts are those n times p's. Okay? It's the sample size times the proportion you would expect to get in that category. So if we think about Skittles, Skittles claims that the colors are equally distributed in every production lot. So they're saying that there are 5 colors of Skittle, so each Skittles color is 1 out of 5, or 20%. So the proportion of orange is 20%, and the proportion of red should be 20%, and the proportion of green is 20%, etc. So 100% divided by 5 colors equally distributed would be 20% of each color. So that is a percentage, not a count. When we talk about observed counts and expected counts, we want a how many number. So if I talk about 150 as my sample size, if I have a sample size of 150, I would expect 20% of each color. So in 150 times p, 0.20, gives me 30. That would be the expected number of each color if they were supposed to be the same. All right, so what I'm going to do is for every observed count, I'm going to find that observed number minus 30 squared divided by 30. So I would have 23, that was the number of red we observed, minus 30 squared divided by 30 plus 28 minus 30, etc. I'm going to do this for every single color. And what this is going to give me is this value of chi-squared, which is 5.067. Okay, that is our chi-squared test statistic. Now, chi-squared test statistic is a little bit different from a z-test statistic or a t-test statistic. Here are the big things you need to know about chi-squared. So first off, chi-squared values are all positive because if you have a chi-squared value of 0, that would mean that there's no difference between your expected count and your observed counts. Or in other words, the sample looked exactly like you thought it should look. There's no discrepancy, there's no variation. And in samples, that hardly ever happens. So theoretically, chi-squared of 0 means that your sample matches your population exactly in its counts, expected counts and proportions, okay? So chi-squared then can only be positive. There are no negative values because you can't match the population more than perfectly, okay? So the farther you get away from 0, the more unusual your sample size is, or the more unusual your sample is with respect to those proportions that we think. So chi-squared are going to have positive values, and it's also skewed to the right. Now, what we do know is that it becomes less skewed and more approximately normal looking, okay, the higher the degrees of freedom. Now, degrees of freedom for chi-squared is going to be k minus 1, where k is the number of categories. So that's going to be a big difference because for t it was n minus 1, where n was the sample size. We're not going to use sample size for this at all. We are interested in the number of categories minus 1. So chi-squared is the number of categories minus 1. So here we go. For Skittles, there are 5 colors. So the degrees of freedom for the Skittles problem would be 5 minus 1, categories minus 1, it would have 4 degrees of freedom. And you can see in the picture over here on the right that the larger the degrees of freedom, or in other words, the more categories you have, the more this chi-squared distribution is going to look less skewed to the right and more mound-shaped symmetric, okay? All right, so chi-squared skewed to the right starts at 0. Just like any other probability situation, our distribution adds up to 1, so the area under the curve is going to add up to 100%, which means we can use it for probabilities. Begins at 0, increases to a peak, approaches horizontally over towards towards positive infinity. All right, so as far as a chi-squared goodness of fit test goes, which is what we're going to do, a goodness of fit test is going to tell us how 100% is split amongst the categories of a variable. So it's going to look like the set of proportions. So when we go to talk about phantoms, okay, the parameters, instead of just having like P is the proportion of yellow, we're going to have P1 is the proportion of yellow, P2 is the proportion of orange, P3 is the proportion of green, P4, P5, etc. So we're going to have several proportions that need to be identified. And our hypotheses, instead of our hypotheses being, say, that P1 equals P2, our hypotheses are going to be like P1 is 20% and P2 is 20% and P3 is 20%. Or maybe it's something like P1 is 50% and P2 is 20% and P3 is 30%. But it's going to show what those percentages ought to be. Okay? So it's just like a one proportion test in the way it's set up. You just have access to everything. The assumptions and conditions are very, very similar. You need to make sure that your observed counts come from a random sample, and you need to make sure your sample size is less than 10% of your population size if you're sampling without replacement. There is one tiny little detail that is different. Your expected counts, since we're testing all expected counts, we need all expected counts to be at least 5. So instead of n times p greater than 10, we want all of our n times p's to be at least 5, okay? Now, when we're talking about the p-value, since chi-squared is skewed to the right, and since we're talking about the more unusual it is, the farther that chi-squared test statistic will be away from 0, these are always kind of like a right-tailed test in that the p-value is going to be the probability of getting a test statistic like ours or more extreme. That more extreme is always going to be to the right. So we will still use that chi-squared test statistic as our T for phantoms, and we'll still have the p-value, which is the probability of getting that result, and we'll use that to reject or fail to reject the null hypothesis. And just like before, we will do this in our TI Inspire. Okay, so if I'm going to set up this chi-squared goodness of fit test, here's how it works. All right, so we would start off and we have a problem like a marketing analyst wishes to see whether consumers have any preference among 5 flavors of a new fruit candy, Star Sours. A random sample of 100 customers were asked their favorite flavor of the Star Sours candy. The results are listed in the table below. Okay, it says test the appropriate hypotheses at the 5% level of significance. So here's the first thing that we would do. You need to recognize that these flavors up here represent observed counts. So when they say the sample counts, that is what is observed. Okay, we also need to figure out what the expected counts would be. So we would think no preference means that they like them all the same. And if they like them all the same and you're splitting 100% into 5 categories, that would be 20% each. Okay, so we're going to start off with identifying our variables. So I'm going to say something like this. Let PC, PA, PO, PL, PG equals the true proportion of customers who prefer cherry, apple, orange, lime, and grape, respectively. Now you can also say PC is the true proportion of customers who prefer cherry. PA is the true proportion of customers who prefer apple. PO is the etc. I mean, so you could list them out separately, or you can use this list with the respectively at the end. Okay, my null hypothesis for this situation, since we're saying that all the proportions are the same, is that each of these proportions will be equal to 20%. And again, you could also list these out separately. PC equals 0.2, PA equals 0.2, PO equals 0.2, etc. Okay, for the alternate hypothesis, here's our alternate hypothesis. It's basically, hey, Ho is wrong. Okay, so at least one of the proportions in Ho is incorrect. That's going to be our alternate hypothesis. Hey, at least one of these, wrong. Okay, so if they're all equal, that means there is a preference. If there is no preference, and if they're not, there isn't. So customers were randomly selected. Okay, true, stated in the problem. Is 100 less than 10% of all Star Sours customers? That is reasonable. And then the next thing I need to do is I need to check the expected counts. Now, technically, you should check all the expected counts. Okay, all right. But what we're going to do is we're going to check the smallest expected count. Since they're all 20%, they would all be the same. And I'm going to physically show that work. Okay, so I know that there were 100 customers. So I'm going to go 100 times 20%. That's 20. That's greater than or equal to 5. And if the smallest expected count is greater than 5, that means that all expected counts are greater than 5. Okay. The name of this test is a chi-squared goodness of fit test, and its degrees of freedom is going to be categories minus 1, that is 5 minus 1, or 4. Okay, now to get the chi-squared and the p-value, I'm going to put this into my calculator, and here is what it's going to look like. So I'm going to bring up my calculator. I have a new document. Notice it has observed counts and expected counts. In my observed counts, I am going to put in the actual observed counts, the actual counts from the experiment themselves. Here we go. All right. And then for the expected counts, we were expecting there to be 20 of each because we took 100 customers times 20%, and we got 20 for each. Now, in other problems, they may not be the same. For example, if 50% is A and 20% is B or something like that, you may have some different counts here. But I'm going to do this. Once I have my observed and expected, I'm going to run a chi-squared goodness of fit test. I'm going to go Menu, Statistics, and Stat Tests. And I want this one that says chi-squared GOF, goodness of fit. There we go. It's going to ask me where's my observed list. I'm going to pick O for observed. Where's my expected list? There we go. And then it's going to say degrees of freedom, which means you have to know that degrees of freedom is is categories minus 1, which would be 5 minus 1 is 4. Okay, and I'm going to click OK. All right, here is my chi-squared value of 18 and my p-value of 0.001. Also notice the degrees of freedom of 4. All right, so chi-squared 18, p-value 0.001. So since that p-value is very small, less than alpha of 5%, I reject the null hypothesis. There is convincing evidence that there is a preference in flavor among Star Sours candies. Okay, so this is very, very similar to what we've already done. Now, next class, we are going to talk about an example where all the proportions are not the same. They all have some different proportions. So on the next page, there's a different example, which we're going to talk about on Monday. So I will see you next time. In the meantime, try to go in and do as much of this as you can. And remember, this is going to be very similar to what we've done before. Good luck.